Okay. Ladies and gentlemen, dear colleagues, first of all, thank you very much for having me here today. It's a great pleasure to be in Japan and to be in Tokyo, to see old friends and new friends, and to have the opportunity this afternoon to talk in this seminar. Thank you for the very meaningful introduction about this SIP program, which is giving the framework and trying to integrate the things. And in fact, as I'm the first speaker for this afternoon, I would like just to enlarge a little bit the pictures and try to show what are the challenges. So what I will try to do is to review a little bit what are the key problems that we are facing regarding flood management through different examples coming from Europe, but also coming from Asia, and trying to pick up some of the most important elements that we have to focus on for the future, addressing some of the points that you mentioned in your presentation regarding how we can develop better system for monitoring, anticipating, and providing decision support to the decision makers in a very operational way. Let me try to start with few pictures. As you mentioned, Japan is strongly affected by regular disasters. I pick up some few pictures over the last years, maybe just to refresh your memory. We are receiving continuously flow of information with numerous disasters per year. And I'm pretty sure with those pictures you can recognize some of the locations that has been more or less recently affected by those type of situation. You see an example in Asia, but there are also examples in Europe and in China, Greece, and Libya quite recently. If we look at the impact of the losses due to extreme events, and especially related to floods and things, we see that we have a global trend which is increasing. So it's due to the fact that we have a larger number of events, but at the same time, vulnerability of our society has increased. So we have a more sophisticated environment, and of course, when disasters are occurring, then we have a more difficult situation to cope, and then we have higher damages. So those graphs are coming from Munich Re, which is a reinsurance company, which is very well known. And on this graph, you see the four types of events and disaster we are facing. So we have earthquakes, so this is this red first part of the column, which is almost constant over the last 40 years. The green ones are slightly increasing. This is meteorological events. And then you have hydrological events, including floods. And you see the biggest increase has been in this category of the blue ones. In average, in total, we have around 1,000 events per year annually, and this is still increasing. And regarding flooding, we have roughly 400 major events. So what you have on the graph is only the major ones for the reinsurance company, where we are exceeding a quite significant magnitude regarding the damages. And if we go a little bit more deeper in the type of floods that we are facing, the most severe losses are related to severe convective storms that are right now the first disaster regarding the losses now on the financial point of view. So this is a graph which is showing the evolution. As I said, it's an evolution which is related to the climate change, to the variability of the climate, and also of the complexity and the increased vulnerability of our societies and especially urban environments. If we look at the number of extreme events, this is what you have on the slide over there. You see per year how much we have observed major events. So we have shifted over the last years from less than 10 to something which is close to 30. And of course, for 25, we will see how the things will be moving. Of course, it's becoming a priority to try to address this type of situation, to improve resilience of our environment, our society, and try to preserve people, of course, exposed population, and try to preserve economical activities. One slide I would like to use just to introduce a little bit what I will present afterwards is what we have experienced in Libya. So Libya is the north coast of Africa. So in this catchment, so we had an extreme rainfall event in a place which is supposed to be a desert. They are supposed to receive less than 300 millimeters per year. And they receive potentially more than 600 in one night, having a cascading effect, so having the flood damaging two structures, two dams that were supposed to be two reservoirs that were not totally completed. They were collapsing, and afterwards the flood was washing away the downstream part, having more than at least 20,000 people who die in the single night. So the numbers of victims is not completely clear. So it's just to say, in such a type of situation, we are facing the weakness of the preparedness, limited anticipation, limited knowledge, limited assessment of the vulnerability of the environment, and dramatic consequences for the population. I would like just to explain why it's something which is happening and why those extreme rainfall are something that we have to consider more and more. And in average, if you look at the situation, so not only for the Mediterranean Sea or for the European region, the problems are coming when we have an intensity which is higher than 70 millimeters per hour. If I was doing the work for comparing the regulation in the different countries, for example, in India, where you reach this 70 millimeters per hour, you stop operating the train because you have a problem in the traction of the train, so you may be flooded and you have problem. We have implicit regulation in China also taking into account this aspect of 70 millimeters. So worldwide, we have a kind of agreement. If we exceed 70 millimeters per hour for 1 hour, clearly we will have problem. So in addition to that, we have convective storms that may generate this type of situation and stationary situation. We generate the convective event, and if this event is staying at the same place for a long period, we are pouring a huge quantity of water that may produce quite serious damages. Of course, it's generated basically with warm and humid environments. The main driver is the sea. So this is what we are experiencing right now in Tokyo. We have a very hot summer. The high temperature on the sea will remain for a couple of weeks, couple of months, and potentially when more humid air will come, we will have the possibility to have those important rainfall, which is reinforced by the morphology and the orographic effect in the different catchments. You have one picture of those severe convective storms. You have an idea on those local rainfall could be extremely limited. So we may have something between 3 to 4 square kilometers. I have experiences in Paris at the Charles de Gaulle airport where this type of event was not recorded by the rainfall gauges. You have a runway which is only 4 kilometers, but we had intensive rainfall in between. So it means it was not catched by the rainfall, but it was taking place and flooding the subway tunnel at that place. People were first thinking, oh, this is the leakages of the water supply. No, it was the rain, but the rain was not trapped by the gauges. So we need to realize how it goes and how it may affect the things. So this one was a small video showing how it's moving and how high intensities may happen. So this one is just showing how it's taking place. I'm coming back to the Mediterranean environment, and especially to try to address the situation in the south of France. So we have wet air traveling from the north part of Africa over the Mediterranean Sea, being hugely loaded with humidity, and when it's coming close to the coast, we have orographic effect. So the clouds are going higher, we have condensation and very severe rainfall coming up at the beginning of the autumn and generating massive runoff. In fact, maybe you are not familiar with those type of pictures. We have something which is close to the typhoon and the hurricanes that are more well known around the world. We have what we call Mitigation conditions that were not very much observed in the past, that have been developing over the Mediterranean Sea. Here you see the North African coast, so Tunisia, Morocco, Algeria. And here you see the Spanish coast, and you see the shape over there. So this is the same. This is Italy and the Sicily. So those conditions are happening, and as I said, the main driver is the sea temperature, especially when we have a temperature which is exceeding 24 degrees. So this is the main indicators, and right now most of the monitoring system are focused on the temperature of the sea. If we are in September and October, we still have more than 24 degrees. We have a high risk to have those clouds traveling from the north part of Africa and migrating to the south coast of Europe, with the possibility to generate massive rainfall. Here you have the distribution of those type of events. When we do the reanalysis of the situation in the past, you see that we had during the 40s, the 50s, very few events, but during the 20s, the 2000, from 2000 and 2010s, we had quite a large number of those events, but curiously, it was reducing over the past years. So this is also something we have difficult to analyze, but it was taking place, but now we know that it was happening. I would like now go to example and try to stress what have been the driving conditions generating, I would say, crisis situation and what has been the damages. So the first example I would like to take is one convective event that took place over the French Riviera. So we are between Cannes and Monaco, so Cannes, Nice, and Monaco. So it's roughly 1.5 million people living over there. And we had a rainfall which was about 260 millimeters in less than 3 hours. So we had quite a severe number of people who were dying, 21 people who were dying, and about more than 1 billion direct damages on the different goods and the different things. It took place on one evening. So what you see over there is a video that was recorded during a football match that was cancelled. So it was raining a lot. So you see in the soccer field, so it was impossible for the player to do. And one of the first mistakes was to announce to the speakers that the football match is cancelled, and then they can go back home, not staying in the stadium. They were safe in the stadium, but everyone rushed to the car, and we had a major traffic jam, and people were potentially exposed to flooding just because they were taking the car for evacuating the stadium. At the same time, due to the traffic, the crisis center, which was supposed to take care and to manage the different teams, were not accessible to the people who were supposed to be and to rush to the emergency centers. So they were not able to operate in good conditions. Regarding the precipitation, so we are talking about 50 kilometers long from Cannes to Monaco, as I said, and we had a huge diversity of precipitation, almost 200 millimeters for Cannes, and less, around 100 for the cities neighboring Nice and Monaco. So this is something that was already observed in the past. This is not unique. We had already in the past rainfall events with more than 100 millimeters in one day. It's supposed to be exceptional, but not at that place with severe consequences. This one is the entrance of the train station. So the train station, the entrance of the train station was totally flooded, and you can see those infrastructures were absolutely not prepared. So it gives you an idea on how the event was developing along the coast, traveling from the west and going to the east. You see the electric activity over there. The lighting were quite intense, especially in this region. So this is where we had the highest intensity. And I will show you the consequences. So Nice is called one of the garden city of the French Riviera. So this is not densely populated. You have quite a lot of gardens and so on. But nevertheless, this is how the conditions were within the street. So high velocity because it's steepy, and people were, I would say, being brave or totally stupid to try to cross and going within the water. We have almost every 2 years 2 or 3 people who are dying just because they are washed away by the water, which is too fast, 2 or 3 meters per second. So with 20 centimeters, you cannot resist, you are washed away. And most of them are trapped within the drainage system because most of the covers of the manhole are open due to the pressure. They fall down inside and they are trapped within the system. So it's happening every 2 years. So this is one of the key problems that we have, which is just prevention, preparedness of the population, being ready in such a type of things. Infrastructures. So this one is just one movie showing how it was in the Cannes Movie Festival. You know, every year we have this festival taking place in Cannes, and you see obviously how it was within the basement of the building. You see the pressure in the drainage system, concrete that was totally destroyed, and of course affecting the basement of the building. Most of the victims, I'm talking about the 21 that have been dying during this event, were people trying to rescue their car in the basement of the building, their car or their mobiles. Phone, or not the mobile phone, but their bicycle and the other things they were willing to rescue. So this is something which is also a problem of education, and you will see afterwards that this situation was repeated, unfortunately, in Spain last year during the Valencia episode. So here, this is, as I said, the entrance of the subway, of the station in Cannes. Here, this is another parking lot where we had several victims, consequences regarding the car, obviously, but also as the sediment transport, as it is steepy, we have a huge quantity of sediments that were mobilized, and during this event we had difficulty to recover, especially for the water supply system, because most of the drainage and drainage system were destroyed during this, and we had not, I would say, few days before to recover for the water supply, but several weeks before to clean up and to be sure that we can operate properly the thing. So this is one of the things which is quite important. The crisis for the water guys, water utilities, was not few days, but it was several months before to come back to operational situation. So here it's just to say that the situation was not unique. It was taking place in the past, but of course with limited consequences, because at that time we didn't have the same developments in the region, and but the effect on the rivers was almost similar. One of the key points regarding the I would say the quite important impact we had on the population was the fact that we had only an orange alert, which is not the maximum of what we can have. You have the risk map which is produced for France, and you see what was produced for this beginning of October. You see Nice, the region over there, was just orange, with indication to the population, be careful, we may face quite important rainfall during this period, and please be careful and don't go too much outside. But it was not a restriction regarding public activities and so on. The decision was not taken because it was not sufficiently anticipated. One of the problems that we had was the knowledge about the situation. So this is what has been produced with meteorological models, which are quite accurate. We have a very good estimation about the quantity of rain, what that has been taking place during this event, with a model which is about 1 kilometer resolution, which is quite nice. The problem was that in 2015, this result came 24 hours after, because we were not sufficiently powerful in the computational resources to produce this type of results ahead. And then we were not able to issue the proper warning to the population and to have the orange alert turn to the red alert. So that was mainly the story. Now I would like to move to what was happening in 2020, 5 years later. So we had almost a similar event affecting a little bit the upstream part of the catchment, which is coming to Nice. So two small catchment, 400 square kilometers, and another one, 350 kilometers, were affected by this extreme rainfall. We had more than 500 millimeters. I say more than 500, because we do not know how much, because all the rainfall gauges were destroyed, because all the calibration threshold, including the radar, had a maximum that was 500 and nothing above. So it means most of the measuring devices were not catching the maximum intensity that we were facing. So the duration was in total estimated to 24 hours. In fact, we had only 6 hours, very intense. We had hopefully only 9 people who were dying, and of course damages 1.5 billion of the things. What was exceptional during that case? So this is something which is extremely unusual. This is what you have on the screen. It was not one convective cell, but it was 3 convective cells at the same time. Never observed before in Europe. So we have those 3 over there, and staying there for almost 6 hours with intensity higher than 85 millimeters per hour. So this is really extreme, and so it was affecting this part of the catchment. The assumption is that we have around 13 millimeters, so which is one of the highest recorded precipitation, one of the 10 highest recorded precipitation in France. How it was distributed, you have the map of the catchment over there, so it was really affecting this part. The catchment is flowing and reaching the south part where the city of Nice is, and it was affecting deeply the upstream part, affecting communities, affecting infrastructures. Almost 80% of the road and public infrastructures were destroyed during this event. It's obviously opening the question, what do we have to do for the future? Do we have to rebuild as it was, or do we have to ask the population to leave this environment and move to another place? But I will show you first how it was looking. This is a place. Beautiful. It looks like a little bit the Switzerland Alps, almost a very, very green valley. So not something which is mineral, fully covered with vegetation. We have a small stream over there, especially this small river with few cubic meters per second. And this is how it was looking less than 1 hour after the beginning of the rainfall. The small river that was only 5 meters moved to something that was 75 meters wide. And of course, most of the infrastructures, bridges, roads, and so on, were washed away. So at that place, the development of this flow was made with 3 parallel streams that were merging finally. So it means most of the concepts that we have for measuring, for explaining how the flow are organized, do not match the reality of this type of situation. In addition, it was also affecting those communities. So this is an example of one of the small buildings that was destroyed during the events. This is the example of the bridges, how they were collapsing, being clearly too small to resist. Most of those infrastructures were designed more than 70 or 80 years ago. So this is not something that has been made quite recently, but this is something that has been there since years. So this house was one of the ones that was created at the beginning of the 20th century, so it's more than 120 years, and this house will be totally washed away with the 2 people that were living within this building. In fact, the 9 people who were dying during the event were people who were in a dangerous position or member of the rescue teams. So not really people who have been directly exposed to the situation. So here you have a view of the situation just a few hours after the flood itself. The river is back to its original shape, only a few meters wide. And what you see in gray is what has been gained over the extension of the riverbed and being active. Here you have an idea about the quantity of sediment that has been moved. Blocks bigger than 1 cubic meter were moved during the flood. So this is something which is giving you an idea of the magnitude. Buildings, full buildings were traveling and moving. This is stone buildings. This is not something which is light. And one of the wall can just give you an idea about the quantity of stone. The building itself is full of stone that has been transported by the river itself during the event. Many constructions have been washed away. It gives you an idea on how it was. One of the few things that we can say, first, it was really an exceptional event, never recorded over there, totally unknown from the local population. So this is something which is quite important. All monitoring stations, so for water level, for discharges, for rainfall, have been destroyed, totally destroyed. So it means we were supposed to be more equipped and more ready to anticipate those things, but it was not the case. Huge damages on public infrastructures, but limited number of victims for, I would say, mainly 3 reasons. We had, first, a better forecasting system based on observation and on models. The models were very useful. They were more intensively used than in 2015. We had a better efficiency warning procedures, and we had especially a better understanding due to the floods that we had in 2015, 5 years. We learned from the previous experience, and population was more aware about what to do and what not to do. Nobody was going to try to rescue a car or a bicycle during these events. So it was the case in 2015, but in 2020, hopefully, the things were better. We did better regarding the forecast. This is a meteorological analysis that was produced 1 day before and a few hours. So clearly the event was identified and sufficient to say something big will be happening. The estimation that was produced by the Met Services was to say something higher than 300 millimeters. We had 500, but at least 300 millimeters is a threshold which is sufficient to say it will be big, it will be exceptional, then you have to move from the orange alert to the red alert. You can take the risk. So that was I would say, a huge improvement. So here it's showing how it was, and we were able to give ahead, 24 hours ahead, a good prediction about the event, and it was sufficient. The management alert procedures. So in fact, we anticipate on September 29th, we identified a weak risk. It was moving forward to a medium risk 1 day later. And then on the 1st of October, we moved to the first stage of the orange alert. And 6 hours before the real crisis, we had to move to the red alert. Red alert means there is a political decision which is taken to close all public services, to stop the traffic, and to provide information to the population with all communication means to be sure that everyone is aware. And you see the map, if you compare with the previous one, we have now this red alert that was provided and that was operational for informing the population. So that was something extremely better than in the previous case and much more efficient for the population. So now what do we have to do? So we have to define a strategy for addressing this type of situation. So what do we do if we have, again, more than 500 millimeters in 5 hours? And one of the key points is to try to simulate the unexpected. It's impossible to us to recreate infrastructures not taking into account the previous engineering hypothesis and moving to 500 because it's just too big, too much money for small rural communities. But the challenge will be to try to anticipate and to say, if this type of situation is happening, the flooding will be such a magnitude and will affect this and this and this region. Be prepared, anticipate, try to locate less essential activities in those places. But this is a debate. This is a debate right now going on. We are almost 5 years after the catastrophic situation, and there are still discussions among the different political entities to see how the management should be organized. Some of the key lessons are, of course, to try to improve preparedness. Better reaction of the population was due to the previous events, obviously, and try to anticipate exceptional situations. So try to have more information on the different situation, and try to be ready to answer, and try to communicate in an efficient way to the population, to the engineers, and to the people who are in charge of the emergency operation. The example I would like to take is the example of Germany in July 2021. I don't know if you remember, but at this period, it was during summer, so we had a quite severe rainfall event taking place in the northwest part of Europe. So we are in France, Belgium, Germany over there, and the rainfall took place over there. I'm not talking about extreme rainfall. It's only 150 millimeters, so over 2 days, but with dramatic consequences, as you can see over there. So we had massive runoff and dramatic consequences for the population. 181 people died during the event, mainly because the people refused to evacuate. They refused to evacuate because they never saw anything like that in those villages, and people were not ready to believe that it may happen. They were saying, we are in our house. Our house is there since 300 years. There is no problem. We will not suffer. We will not be affected by the event. But unfortunately, it was the case. Damages, 10 billion euro. It's still the highest cost related to flood worldwide. Of course, the new one in Valencia as maybe will be higher than that. I will come to this point. But something which is very interesting, we did with a colleague this work to try to assess what has been the condition in the past. You have the pictures of July 2021, and you have the pictures taken in 1910. Same location, same effect, same infrastructures. Bridges, railway track, they have been destroyed, rebuilt exactly as they were, and the same effect has been taking place. We were digging a little bit in the archives, and we saw that in 1804, we had an event which was almost twice bigger than 2021. So it means it's not only the climate change and the new condition, but in the past, we had such exceptional situation that should be considered. And of course, it's questioning how we do the design of the infrastructures, how the design are ready to face this type of exceptional condition. To do the transition And before to move to Spain, I would like to show you what was happening in Zhengzhou, in Henan province in China. So they had more than 500 millimeters in the new city of Zhengzhou with catastrophic consequences because those conditions more than 200 millimeters per hour, so which is an extremely high intensity, were never considered for the design of the infrastructures. So you have an access road for the for highway, but more dramatic was the condition regarding the subway operation that was not designed and that was continuing to operate within the flooding. So many people were dying within the subway. More than 300 people were dying during this event. So it's extremely difficult to manage this condition. And as I said, the design was made according to the code, according to the references, but nobody took in mind the possibility to face such a tremendous situation. Of course, if we want to improve the things, and one of the things that has been demonstrated with the case I was showing on the French Riviera was the fact that we can use models. One of the key points when you are trying different type of models for producing and to anticipate the things, I strongly believe that we still have to work on deterministic approach, just because we cannot anticipate extreme conditions. They are not recorded, they are not in the data, so we still have to produce deterministic approach before to be able to implement AI solution or data-driven solution. So this is the example. So the idea is to try to simulate the behavior of the catchment, the surface, the runoff, and to see what has been the consequences of the extreme things. We did the work for the Var River. If you remember, the extreme rainfall in 2020 was affecting this upstream part of the catchment. And the idea was to try to produce the hydrograph and to reproduce how the flood was moving down and reaching the city of Nice, which is located downstream. You see the situation of the river. This is quite serious. We are talking about 4,000 cubic meters per second flowing down and moving. So this is quite impressive. Strong load of sediments, almost 3 meters of water plus 2 to 3 meters of sediments moving at the bottom of the river due to the steep slope, and this is quite difficult to control. The shape of the hydrograph is extremely sharp, so we had something which was below 50 cubic meters per second and moving up to something quite high in those different locations. Major contribution was coming from the VSUB. And you see downstream how the hydrograph is taking place. So more than 1,000 cubic meters were coming from this river and moving down. And this is what we have obtained. The blue one is what has been recorded, partly affected by the measurements conditions that were not good, and also due to the fact that the measurement devices was afterwards washed away and destroyed. So we have a partial view, but at least with the model we can reproduce the things in a proper way. What is now interesting is when we are using those data and when we are comparing the results with different type of models. So here what you have is a benchmark of 12 models, where we have 3 deterministic models plus 12 data-driven models. And as you can see, you have a huge diversity on the results. And the only ones that are performing well are the 3 deterministic models that are bringing something which is consistent, at least regarding the magnitude of the things. And obviously, some of the other data-driven models were not able to perform well just because they've never been trained with those extreme things. So models can be interesting to train, to produce exceptional data before to use the AI technology. Let me now move to the final example I would like to share with you, which is the one that took place in Valencia in Spain last year. I'm pretty sure that you remember. We are in a very similar situation. So about 46 square kilometers, the city of Valencia is here. This is the Mediterranean Sea. We had a huge rainfall over this catchments with absolutely tremendous consequences. You see where's the flow within the rivers. You see the consequence over the city. You see devastation of the infrastructures. You see how it was over there. Collection of cars being transported and accumulated within the streets. Colleagues are now trying to model how the cars are accumulated in the different streets to try to anticipate the rescue operation, which is quite important. The event was more extreme than before. We had more than 700 millimeters in a single day, so almost 5 hours, so which is something which is extremely huge. So it was raining mainly in the upstream part of the catchment, where there is a very light monitoring system. So it means here the rainfall was taking place, but in Valencia itself, almost zero. So most of the people were not aware about what's going on, and no real information was propagated and sent to the population on time. And this is one of the weaknesses of the story. We had a maximum rainfall intensity which was higher than 180 millimeters per hour, so which is really, really, really extreme. You get an idea on how it was distributed. And here you have an idea on how it was flooding the city and how it was affecting the urban environment. So the small stream, which is almost dry most of the year, moved to something which was close above 4,000 cubic meters per second. So the return period for this event is assumed to be higher than 500 years. It was perfectly known because few years before this assessment on the catchment was the analysis was done, the flood map was produced, and what you see over there is a comparison between what has been produced for the flood map in blue and what has been the extension during the event. It's matching almost nicely, except few places where you had extra damages on the infrastructures. When you get a road, which is like a dike, when this road is broken, the water is moving another part of the city, which has not been assessed as a potential flooding area within the things. Conclusion of Valencia, more than 300,000 people have been affected, so which is quite high. More than 500 people died during this event. 11,000 houses. One of the key problems they are facing right now is the elevators. Elevators are out of work, of course, due to the disturbance of the devices. But more seriously, there is no spare devices available in Spain and for most of the constructors in Europe. So it means even right now, we are 1 year later, most of the elevators have not recovered, and for some places, this is a key point. Damages on industry, number of cars affected, and the total for direct damages is 17 billion euros, so it starts to be really, really big. And of course, there is a need to try to anticipate the things. How to try to anticipate, and it will be in some extent the conclusion of this presentation. So we have to develop efficient forecasting system, and I think your program is really targeting that. We have to create this early warning system, which is robust. I will repeat it 3 times, robust, 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 because in a severe condition, we have to face situations that were not defined during the design of the things. And we need to keep in mind the possibility to assess, never observe extreme situation, just to anticipate and to prepare the population. I think this is quite important. We need to try to develop resilience, obviously, and we need to develop the resilience at the right scale. Not only the resilience at the scale of the city, but the resilience at the scale of the region. We have observed that in many crises, the reaction of the local team is always too late to ask for help from the other cities. But we must have a mechanism which is automating this process, being sure that when we exceed the threshold, we mobilize not only at the city level, but in a wider scale to be sure that the people will participate. There is a willingness to rebuild after the crisis. How do we rebuild public infrastructures? This is a huge debate. Do we rebuild exactly as it was? We need to quantify resilience. Flood resilience index is something which is quite important. In Europe, we are promoting resilience plan by 2030, which are supposed to help the different member states to recreate more resilient environment and to be prepared for this type of message. Last slide, which is the key message for you and maybe for future research and collaboration. Convective events are really new challenges. From the example I presented, I'm pretty sure now you understand the challenge that are not only for Europe, but I'm pretty sure in Japan you are facing exactly the same type of situation. It's clear that we can never be flood safe, and it's extremely dangerous to believe that we are flood safe. So whatever is the protection, it may fail, and we may have an extreme situation that we were not prepared to. We need to anticipate those situations and providing information to the population. Sharing this information to the exposed population is really the key point. And finally, trying to improve the resilience of urban environments. It's not only for the current urban environment, but clearly for the design of the future of the urban environment. Japan is experiencing reduction of population in the future. You will have to rethink the organization of your cities and maybe to prepare your city to be more ready to face such a type of environment. So this is something that should be done not only at the scale of the building, but at the scale of the block and of the district. So with that, I was already too long, but I would like to thank you for listening to this presentation. Thank you very much.
Professor Gourbesville, thank you very much for your insightful presentation.